we learned the basics of electricity. We learned that there is a property that exists in electrons and protons, and this property is called charge. They also have mass, which is another property, but specifically we were talking about the property of charge. There's two versions of it. There's a negative and there's a positive. The electrons carry the negative and the protons carry the positive. If I transfer electrons, if I take away electrons from an object overall, that object becomes a positively charged object. If I add electrons to an object, then that object becomes a negatively charged object. And charged objects exert forces on each other. They have an effect. They can attract if the charged objects are opposite. And if the charged objects are the same, they will repel each other. So they can cause objects to move. We saw that we could transfer electrons by friction, by contact with a charged object, or by induction. And that creates something on the outside of objects, which is called a static charge. And static charge isn't very useful. We can't make it do much work for us. We can also make charge move, and that's current electricity. Current electricity is very useful. That's the kind of electricity that we use to light our houses, that we use to play our music, to play our TVs, to heat our homes, to air condition our homes. So we depend on current electricity. So we want to see, why is it that electrons will move? What makes them want to move? And we have to look at this idea of electric fields and potential. The big idea for the chapter is that an electric field is a storehouse of energy, and then we can use that energy to do work for us. So an electric field is a storehouse of energy. Energy is useful because it can do work for us. Static electricity isn't very useful, but energy in motion is useful. The first thing we want to look at is this concept of a force field, and it actually is just the space around an object. The space around a magnet, if I have a magnet sitting on the table, looks empty. But I know if I put another magnet near it, it can push away that other magnet, or it may pull that other magnet, but it can make the other magnet move. So there is something around the magnets, even though it looks like empty space, that is actually having an effect. And we call, because that space has an effect, we call it a force field. Objects, because of their mass, have a gravitational force field, and electrical charges, the space around them that can have an effect, is called an electric force field. So objects don't have to necessarily be touching each other to exert forces. For me to move a chair or to move a desk, I have to actually touch it. But for the earth to bring a ball back that's tossed into the air, to bring a ball back down to earth, the earth doesn't have to touch the ball. There's no invisible fingers that are attached to the ball that's bringing it back to earth. But there is something around the earth that must be acting on the ball, and that something is the force field. It seems like the ball and the earth are acting without touching. We call that action at a distance, where it appears that they are not touching. But actually, what is touching is the ball is touching the force field. So if we think of this as the earth and this is the ball in the air, there's something here, invisible, that has an effect on the ball. This invisible something around the Earth is called the gravitational force field. Around electric charges, that space is called an electric force field. It's that electric force field that holds an electron in orbit around a proton. The forces seem to be acting at a distance, but what's really touching is the electric charge of one object is touching the force field of the other. There is contact between the charge and the field of the other charge. So if I have a positive nucleus and I have this electron out here, they're not touching, but they're each touching the force field of the other. So around this positive, there's this space. It looks invisible, but it has an effect on this electron. It's attracting it. And around the electron, it has a field. And it's pulling the proton towards it. So they're not touching each other, they're touching the force field of one another. So electric field has strength and it acts in a certain direction. It has a direction. It either is able to push objects away or it pulls them. So objects move in the force field. The strength of an electric force field can be measured by what it does to charged objects that are in the field. And we use a positive test charge to see what effect the force field has. So what this means is that if I have a positive charge here, well, let's say that I have, let's do this. Let's say that I have a charged object, and I don't know what the charge is. If I put a positive charge here as my test charge, and it's pulled inward, and I put a positive charge over here, and it's pulled inward, and I put a positive charge here, and it's pulled inward, and I put a positive here, it's pulled inward, and it's put a positive here, and it's pulled inward. The same thing happens no matter where I put this positive charge, it's pulled inward. What would you guess is the charge on this object? If you said negative, you're right, because it pulls the positive test charge towards it. If I have another charged object over here and I put my test charge, which is always a positive, and I see that it moves outward, and if I put it here and I see that it moves outward, and I put it here and it moves outward, and I put it here and it moves outward, what would you guess the charge is on this object? If you said positive, you're right. So scientists agreed to always use a positive test charge to see what happens in this space around the charged object. And then we use these arrows to represent that the path the positive test charge would take. And these are called field lines or lines of force, and they describe what happens they describe the force field. What if I had two positives? What would a positive test charge do? Well, it would be pushed away, but at a certain point, it's also going to be pushed away from this direction. So what happens is it's pushed away from both of them. And if I put a positive test charge here, it's going to be pushed away from this one, and then it's going to be pushed away from the other, and it's going to go like this. If I put a positive test charge here, it's going to be pushed away. It's going to be pushed away, and it's pushed away by the other one, so it would go out. If I put a positive here, it's going to be pushed away, but when it gets in the other force field, it's going to be pushed away from that one. So these lines can describe what happens around these charged objects. And I'm drawing the lines because it's what would happen to a positive test charge. It's going to move outward until it gets into the force field of the other charged object, and then it's going to be pushed away from that. So the pattern is that they would repel each other. If I had a positive and a negative, and I put a positive test charge here, it's going to be pushed away from the positive and drawn towards the negative. If I put it up here, it's going to be pushed away until it gets into the force field of the negative, and then it's going to be pulled towards it. If I put it here, it's going to be pushed away from the positive, and then when it gets in the force field of the negative, it's going to be pulled towards it. And I could do that over, oops, what did that do? I could do that over and over, and I would see that this would describe the force field. If I put a positive here, it's just going to go out. I'm sorry, it's going to be drawn in. What am I talking about? If I put it here, it's going to be drawn in. If I put it here, it's going to be drawn in. If I put it here, a positive is going to be pushed away until it gets into the force field of the negative, and then it will be pulled inward. So we get this pattern that describes that space. This pattern of lines describes that empty space. It's not empty because there's a force acting in that space. Where the field is strongest, the force field on the test charge is strongest. Where the field is weakest, the force on the test charge is the weakest. The direction of the field is the direction that a positive test charge would move. These lines that I was drawing are arrows. A vector is an arrow, and the vector shows the strength of the force field and the direction. And they're used to describe that space around a charged object. We use field lines. They're also called lines of force to represent the electric field. If the lines are farther apart, that means the field is weaker. They show the pattern of the force field. They're arrows, so they show the direction of a positive test charge. If the lines are closer, that means the field is stronger. And the force field lines never cross. All right, I need to do this. Oh, that's not the right one. So this looks like an empty space, and I'm going to put a negative charge in this empty space. And I want to see what my positive test charge would do. Why it's going to be drawn towards the negative. And what would this one do? It's going to be drawn towards the negative. And what's this one that's a little bit closer? Notice that it has a longer arrow here, which indicates that the force is stronger. This arrow is a vector. This arrow is a vector. And it shows the direction and it shows the strength. So the closer it is, the stronger the force is. The length of the arrow just means it's drawn inward with that much force. As I move it away, the force gets weaker. The arrow gets shorter to show that it's not as strong. The closer it is, the stronger the force is that's pulling it. Okay? So this is our negative. Oops, sorry. So this is our negative, and notice that all the arrows point inward because a positive test charge would move towards the negative. These arrows are close together here. That means the field is stronger. The arrows are farther apart here, so the field is weaker. In this example, we have the positive test charge, and it's going to be, we have a positive charge, and if I put a test charge here that's positive, it would be pushed outward. Anywhere I'd put that little positive test charge, it's going to be pushed outward. So the field is strongest closer in, and it's weaker, and the arrows are farther apart as we go outward. But the arrows point outward because that's where a positive test charge would go. In this animation, we have two charged objects. We have a negative on the left and a positive on the left and a negative on the right. So if I had a single positive charge here, it would, go away from the positive and towards the negative. And if I did that over and over, I would get that pattern of field lines. This is what the pattern would look like if both of the charges were positive. What would it look like if they were both negative? If I had negative, negative, a positive charge would be pulled inward. Positive charge over here would be pulled inward. If it's up here, it's going to be kind of pulled towards this one on the left, but more towards this one on the right. So it kind of curves. This one is going to, if I put it here, it would be pulled kind of towards the one on the left, but more towards the one on the right. And if I did this over and over, I would get a similar pattern as I had up here, except all the arrows would point inward. So again, in the middle, they're repelling. So if I put a test charge here, it's going to be kind of pulled to the left, but more to the right. Kind of to the left, but more to the, kind of to the right, but more to the left. So that's this idea of the field lines. If I had two plates, one was positive, one was negative, the arrows would point towards the negative because that's the way a positive test charge would move. Last idea we're going to talk about real briefly is electric shielding. Someone had asked a question. Why are you safe inside a metal car that's struck by lightning? You might think it's because of the rubber tires, but the lightning hits the metal first. So what happens inside the car? Why are you safe inside of there? Electrons from the lightning bolt, first of all, repel each other, and they're going to spread out, oops, sorry. They're going to spread out evenly all around the car. I'm sorry. So all the electrons are spread out evenly around here. So inside the car, there is actually no force field. It's almost to zero, and here's why. Imagine that this is like the outside of the car. So it's hit by lightning, and you have all these electrons. Because this is a metal, they all move as far away from each other as they can, and they spread out evenly around the surface. If I put a positive test charge in the middle, which way is it going to be pulled? It's going to be pulled this way. It's going to be pulled this way and this way. Which way is it going to move? Nowhere, because it's like a tug of war. It's being pulled oppositely equally. It's being pulled this way and this way. So it's not going to move. If there's no movement, there's no force. So inside the car, there's no electric field. A test charge inside this conductor would be pulled evenly in all directions. And so there's no net force. And so there's no electric field. We use this idea to shield electric components. We actually put them inside metal boxes. Inside the metal box, they're protected because there's no electric force field. So they're protected from all the electricity on the outside. So your components for your computer, I don't want them being interfered by static charges on the outside or other electric forces that might be nearby. I want them protected, so I put them inside a metal box, which sounds counterintuitive. You would think that you would not put metal around things that you want to protect from electricity, but being inside the metal, you're inside an area where there's no force field, because the metal takes all the electrons on the outside and evenly spreads them out. So if there's any extra electrical out here, it's not going to have any effect on what's inside, if that makes any sense. So we're going to stop there. My question is, what kind of a test charge is used to determine a force field? And the other question is, that's number one. Number two is, what do the arrows show that are drawn to indicate a force field? Two things that the arrows indicate about the force field.